Welcome to lectures for diploma students. In today's lecture, we are going to deal with some of the fundamental definitions of alternating waveform. The shape obtained by plotting the instantaneous ordinate values of either voltage or current against time is called an AC waveform. An AC waveform is constantly changing its polarity every half cycle and alternating between a positive maximum value and a negative maximum value respectively with respect to time. The sinusoidal waveform or sine wave is a fundamental type of alternating current and alternating voltage. It is also referred to as a sinusoidal wave or simply a sinusoid. The electrical service provided by the electricity board is in the form of a sinusoidal voltage or current. So, these are the typical diagrams of sinusoidal signals. This is called as a sine wave, this is a complex wave, this is a triangular wave and this is the square wave which alternates both in positive and negative half cycles. So, it is one of the definitions of AC waveform, instantaneous value. So, there are several values in AC terminology. One is the instantaneous value of voltage, RMS value of voltage, average value, then peak value, then peak to peak value and so on. So, first of its kind is instantaneous value. So, let us see what the meaning of instantaneous value is. The value of an alternating quantity at any instant is called instantaneous value. They are represented by small letters I, small v, small e, etc. Suppose if you have a sinusoidal signal like this. So, if I calculate the voltage at a particular time t, it is called as at time t, what is the value of voltage? So, this is the corresponding voltage V. So, that is called the instantaneous value at time t. Suppose if I calculate value of voltage at time t is equal to T1, then it is called as the instantaneous value which is equal to V1. So, the expression of instantaneous value of current I is equal to Im sin theta, or we can represent that as Im sin omega t. We can substitute this is called as angular velocity, this omega term is called as angular velocity, for which we can substitute 2 pi f value instead of omega, where f is the frequency of the alternating signal. Then expression for instantaneous value of voltage V is equal to Vm sin theta or Vm sin omega t or Vm sin 2 pi f into t, where Vm is the maximum value of the voltage. Then comes the amplitude. So, it is the highest value obtained by the current or voltages in half cycle, either positive or negative half cycle of an alternating quantity. So, this is an alternating voltage. So, this is the amplitude. It can be either a voltage or a current. Then comes cycle. One complete set of positive and negative value of an alternating quantity is called a cycle. So, one positive half cycle and one negative half cycle together constitute one cycle. Then time period. The time required for a sine wave to complete one full cycle is called time period. T is equal to 1 by f second, or it can be expressed in millisecond also. F is the frequency. The period of a sine wave can be measured from 0 crossing to the next corresponding 0 crossing as shown in this figure. So, this is first 0 crossing, then this is next one where first half cycle, that is positive half cycle, is completed, and then this is the place where the first negative half cycle is completed. So, this is called as period. The period can also be measured from any peak in a given cycle to the corresponding peak in the next cycle. So, the example is this. This is how we can measure from this peak to this peak. So, this is called as one cycle. Then comes the frequency. So, it is a reciprocal of the time period. Frequency is the number of cycles that a wave completes per second. It is represented by f, its unit is hertz. 1 hertz is equal to 1 cycle per second. So, in the domestic supply, if you measure the frequency is going to be 50 hertz, it means that the time period is equal to 1 by 50, which is equal to 0.02 second. It means that the sine wave takes 0.02 second to complete one full cycle, or if you take 1 second, if you capture the alternating waveform in the CRO, that is cathode ray oscilloscope, you can find 50 such waves in a single second, that is in 1 second you can find 50 cycles. So, that is the meaning of frequency. This is the relationship between frequency and time. So, the frequency is equal to 1 by time period, or the time period is equal to 1 by frequency. Time period is expressed in seconds, whereas frequency is expressed in terms of hertz. Then comes the peak value or the maximum value. The peak value of a sine wave is the value of voltage or current at the positive or the negative maximum with respect to 0. So, this is the peak. So, this is the positive peak and this is the negative peak. So, positive peak is plus V p, negative is minus V p. Since the positive and negative peak values are equal in magnitude, a sine wave is characterized by a single peak value. It is represented by V p or I p. Then peak to peak value. The peak to peak value of a sine wave is a voltage or current from the positive peak to the negative peak. It is always twice the peak value. It is represented by V p p or I p p. So, this is your peak to peak voltage, whereas this is the peak voltage. Then comes the average value or mean value. This is the average of the instantaneous values of an alternating quantity over one complete cycle of the AC waveform. It is also known as the mean value. To obtain the average, divide the period into n equal intervals. At these individual intervals, let the current be I 1, I 2, I 3 and so on up to I n. So, we can have a cycle like this. So, each instant what is the value of voltage you calculate, say for example, this is V 1, V 2, then V 3 and so on up to V n, and finally with these instantaneous values you can easily calculate the average value with the help of these two formulae. So, one is I average is equal to I 1 plus I 2 plus I 3 up to I n divided by n instantaneous values, that is how the whole time period is divided into n samples. So, you should divide that by n. Similarly, you can obtain the average value of voltage also. Average value can also be defined as the ratio of total area under one half cycle to the base period. So, average value in general can be expressed by area under the curve of half cycle divided by base of the half cycle. Expression for average value of sine wave. We know that the instantaneous value of current is given by the expression I is equal to I m sin theta. So, where I m is the maximum or the peak value of the current. Consider an elementary strip of width d theta in the first half cycle of the current wave. Let I be the mid ordinate of the strip, then the area of the strip is given by I into d theta. Then the area under the curve for half cycle is, so when you find out the average value, so this is your sinusoidal signal. So, this is your 0 degree and this is pi and 2 pi. So, if you integrate right from 0 to 2 pi, so the positive half cycle and negative half cycle values will cancel each other and the average value will become 0. So, to avoid that, what we are going to do is we are going to apply the limits right from 0 to pi, not 2 pi. So, the limits will be 0 to pi and then I m sin omega sin theta d theta. You take this I m out because it is a constant value, then we are going to integrate sin theta with respect to theta. So, upon integrating this you will get minus cos theta, you apply the limits. So, minus cos pi minus of minus cos 0. So, cos pi is minus 1. So, minus into minus plus, then minus of minus cos 0 is 1, you get 2 Im. So, it is the area under the curve for half cycle. Then the average value is equal to area of the half cycle divided by base length of half wave. So, base length of half wave, as I have already told you, it is pi. So, upon calculation you get average value of current is equal to 0.637 Im, 0.637 Im. It means that, so when Im is equal to 100 value, so I average would be 63.7. So, that is the meaning. So, it is 63.7 percentage of the peak value will be your average current. Similarly, average voltage is equal to 63.7 percentage of the peak value. Then comes the root mean square value. The root mean square value of an alternating current is given by the steady DC current which produces the same heat as that produced by the alternating current in a given time and given resistance. To obtain the average, divide the period into n equal intervals. At these interval, the currents are I1, I2 up to In. Thus, the RMS value of the current and voltages are given as follows. Now, you can very well compare this with the average value. Average value, what we are doing is, we are just taking the algebraic sum of all the instantaneous value of currents or the instantaneous values of voltage, that divided by the n samples. Whereas, here in IRMS what we are going to do is, we are going to square the value of instantaneous current or voltage, and then we are going to add the each individual squared value of the components and then dividing it by the number of samples, that is the base value. We get RMS value of current as well as RMS value of voltage. So, in general RMS value is also defined as RMS value is equal to square root of area under the squared curve divided by base length or period. The expression for RMS value is equal to instantaneous value of current, which is equal to Im sin theta, where theta is equal to omega t, that is in terms of time samples. Consider an elementary strip of width d theta in the first half cycle of current wave. Let I square be the mid ordinate of the strip, then the area of the strip is equal to I square d theta. So, what we are going to do is, we are going to take the square of the instantaneous value. We have already seen that the instantaneous value is I is equal to Im sin theta. So, we are going to square it. Now, you can see while calculating the average value, we have taken the integration right from 0 to pi, whereas we are going to take the integration from 0 to 2 pi in this case, because we are going to square it here. Now, Im square is a constant value which is taken out, then sin square theta is equal, sin square theta is equal to 1 minus cos 2 theta divided by 2, substituting that value here, then 1 by 2 minus cos 2 theta by 2, then d theta. Upon integration we have theta by 2 minus, when you integrate cos 2 theta by 2, you will get sin 2 theta by 2, already there is a 2 over here. So, 2 into 2 will be 4. So, then applying the limits we get Im square into pi, then IRMS is equal to area under the squared curve divided by base length or period, which is given by Im square pi divided by 2 pi, which is equal to Im by root 2, or we can say IRMS is equal to, that is I root mean square value is equal to 0.707 into Im, where Im is the peak value of the alternating current, or I can say whenever you have the peak value as 100 units, then your RMS value will be 70.7% of your peak value. So, by comparing this value with your average value of any alternating quantity will be much lesser than the RMS value. Similarly, RMS value of voltage we can find out, Vrms is equal to 0.707 into peak value, that is 70.7 percentage of the peak value will be the RMS value. Then form factor, it is defined as the ratio of RMS value to the average value of alternating current or voltage. Form factor is equal to RMS value by average value. Already we found that RMS value is equal to Im by root 2 and average value is equal to 2 Am by pi. So, upon simplifying this we get the value as 1.11. Then peak factor, it is defined as the ratio of the maximum value to the RMS value of alternating current or voltage. So, the maximum value is Im divided by the RMS value is Im by root 2, we get a value of 1.414 or root 2. Now, let us do a problem on the various fundamental units of AC waveform. Here the alternating current passing through a circuit is given by I is equal to 141.4 sin 314.2 t. Calculate the maximum value, that is Im you need to calculate, then RMS value, that is IRMS, then the frequency of the alternating current, alternating voltage, the instantaneous value of the current when t is equal to 0.02 second. So, what we are going to do is we need to find out the maximum value, then RMS value of the voltage, then the frequency of the alternating voltage, and then the instantaneous value at time t is equal to 0. Suppose if you have a alternating voltage like this is time t is equal to 0.02. So, corresponding to this time, what is the value of voltage you need to find out. So, that is Vt. Now, the maximum value is inferred from the equation itself. So, I is equal to 141.4 sin 314.2 t. So, Im is equal to, straight away it is 141.4, that is the peak value. RMS value, already we found out the expression for RMS value, which is Im by root 2. So, mere substitution of 141.4 divided by 2 will give you IRMS, which is equal to 100 amperes. And then we need to find out the frequency of the alternating voltage, for which we should know the value of omega. So, this is the omega value, which is equal to 314.2, f is equal to 314.2 divided by 2 pi, which yields a value of 50 hertz. Finally, we need to find out the current value when time is equal to 0.02 second, for which we need to substitute the value of time t is equal to 0.02 in the equation given. So, the given equation is I is equal to 141.4 sin 314 t. So, instead of t I am going to substitute 0.02 here, and then calculating you get a value of 0 current. So, the instantaneous value of current at 0.02 is equal to 0, because the frequency is 50. So, whenever the frequency is 50, the time period is 0.02, 1 by 50 will be the time period. So, exactly at 0.02 second, if you see, so this is the time period is 0.02. So, at this point we are going to calculate the value of current, which is 0. Just by seeing the diagram itself, we know that I is equal to 0 exactly at 0.02 second. What is the equation for a sinusoidal current of 25 hertz frequency having RMS value of 40 ampere? So, the given data is RMS value of current is given by 40 ampere, frequency is given by 25 hertz. We need to find out the equation of sinusoidal current. The instantaneous value of current I is equal to Im sin omega t. So, omega is nothing but 2 pi f, omega is equal to 2 pi f, then Im is equal to IRMS into root 2, which is 40 into root 2, which is given by 56.57 ampere. So, this 2 pi f we need to calculate, which is left over here. So, I am going to calculate this, omega is equal to 2 into pi into frequency now is 25. So, 50 into pi, which is 3.14. So, whose value is equal to 157.0. So, this 157 is the angular velocity we need to substitute here. So, I is equal to I m sin omega t, where I m is equal to 56.57, omega is equal to 157. Then comes a very important term called as phase in an alternating voltage. The phase of an alternating quantity at any time t is defined by the angle by which the phasor marks with a reference value. The difference in angle between any two voltages or currents is known as the phase difference. Now, you can see for this is the example given. So, the alternating voltage with a continuous line. So, this is the alternating voltage V 2 with a dotted line. So, this alternating voltage, that is V 1, let us assume this as V 1 and dotted line as V 2. The V 2 starts exactly at 0 degree, attains positive peak at 90 degree, that is pi, and again becomes 0 at 180 degree, that is 2 pi, then attains negative peak at 270 and then coming back to 0 at 360 degrees. The same thing happens in V 2 also, starts from 0, attains positive peak, then 0, negative peak and again 0, but exactly at a different instant of time. Suppose if this starts at t 1, the second one starts at t 2 at a phase angle difference of phi. So, I can say with magnitude, in terms of magnitude, both are same, the peak values are same, everything is same, but the phase difference between V 1 and V 2 is termed as phi, which means that suppose if phi is equal to 30 electrical degrees, now I can say the voltage V 2 lags behind V 1 by 30, or I can say V 1 is leading V 2 by 30 degrees, both are same. So, here you can see here it is V A and V B. Now, both are in phase with each other, both start at exactly at 0 degree, attains positive peak exactly at 90, becomes 0 exactly at 180, becomes negative, that is attains negative peak exactly at 270 and then comes back to 0. So, these two voltages V A and V B are said to be in phase, there is no phase difference between V A and V B, unlike the previous one. You can see, once again we will see it. So, you can see here there is a phase angle difference of phi between V 1 and V 2, though they are exactly equal in magnitude, they have a phase difference, whereas here you can see their magnitudes are not equal, right. So, the peak value of V B is much lesser when compared to the peak value of V A, whereas the phase remains same. Now, you can see this is the third example, V A and V B both are anti-phase with each other, right. The magnitude of V A and V B both are same, but if the phase difference between the two voltages is 180, then they are said to be out of phase or anti-phase. From the figure V A, we can infer that V A and V B are anti-phase with each other, their starting points are same, but when voltage V A reaches its positive peak, V B attains its negative peak. When V B attains its positive peak, then V A attains its negative peak, exactly opposite to each other. So, they are said to be out of phase with each other. Then phase angle, it is defined as the angle between the voltage and current, it is represented by theta. Phase lag, a lagging alternating quantity is one which reaches its maximum value later as compared to another alternating quantity. From the figure, the alternating voltage V B reaches its maximum value or 0 value later by 5 degrees when compared to V A. V A is equal to V m sin omega t and V B is equal to V m sin omega t minus 5. Now, let us see here, since we have a phase angle of phi difference, that is VB is, since VB is lagging behind VA by 30 that is 5 electrical degrees, I can represent VA is equal to Vm sin omega t and VB is equal to Vm sin omega t minus 5, because VB is lagging behind the voltage VA by phi angle. In phasor quantity I can represent this as a, I take this as a reference vector. So, this is VA. So, VB is lagging behind VA by phi. Suppose if you have a reference point, so this is a reference point, if you rotate the phasor in the anticlockwise direction, then VA reaches this reference point first and then VB reaches the reference point at a later time instant after 5 electrical degrees. So, this is the meaning. So, whenever you rotate the phasor in the anticlockwise, VA reaches first the reference point and then after 5 electrical degrees VB will reach. So, I can say VA is leading the voltage VB by an angle phi, or the phasor VB is lagging behind the voltage VA by angle phi. The phasor diagram clearly shows that VB lags VA by an angle phi. A negative sign is used to denote the lagging angle. Suppose if VB leads VA by an angle phi, then this would have been omega t plus phi, because we are taking this VA as a reference vector. Then phase lead. Now you can see in the earlier case VB is lagging behind VA by angle phi, whereas here VB is leading leading VA by angle phi. Now you can see this reference point is here, you rotate this in anti-clockwise direction. Now you can find VB reaches the reference point first and then VA with the phase angle difference of phi. In this case it is entirely different. So, VA is lagging behind VB by phi angle, or VB is leading VA by phi angle. So far we have used phasor diagrams to solve the problems on AC circuits. A phasor diagram is a graphical representation of the phasors of AC circuits and may not yield quick results in case of complex circuits. Engineers have developed techniques to represent a phasor I in an algebraic form. Such a technique is known as phasor algebra or complex algebra. Phasor algebra has provided a relatively simple but powerful tool for obtaining quick solution of AC circuits. It simplifies the mathematical manipulation of phasors to a greater extent. So, we can consider a phasor V lying along the OX axis. So, this is the phasor V, it is the in the axis OX. If you multiply this with phasor by -1, the phasor is reversed, that is it is becoming minus V. So, in other words we can say that it is very equivalent to rotating this V phasor in the other direction, which will yield minus V, that is it is 180 degrees in counterclockwise direction. Suppose if it is rotated in the other way, so that is equivalent of this. So, we arrive at a very important conclusion that when a phasor is multiplied by J, the phasor is rotated through 90 degrees in the counterclockwise direction. Each successive multiplication by J rotates the phasor through an additional 90 degrees in the counterclockwise direction. It is easy to see that multiplying a phasor by J, that is equal to minus that is square root of -1, rotates the phasor by 90 degrees in the counterclockwise direction from OX axis. Multiplying the phasor with J square will yield you 180 degrees counterclockwise direction from OX, and multiplying the phasor with J3 yields 270 degrees counterclockwise direction. So, J4 that is the product of J4 with the phasor will yield you 360 degrees of counterclockwise direction from the OX axis. So, this is how we can analyze all the phasors. Now, we will have a quick recap of whatever we have studied, we have learnt in today's lecture. So, we have seen very important terms like instantaneous value of voltage and current, RMS value of voltage, then peak value, peak to peak value, average value, etc., and we have derived the expressions corresponding to the terminologies what we use in AC circuits. Thank you.